Good morning, I am Anita. I am going to explain about the scaling of MOS circuits. So what is meant by scaling? If you see the feature size of the MOSFET, in 1965 it was around 10 micrometer, whereas in 2005 it has come down to 90 nanometer. That means the size of the MOSFET is shrinking or scaling. So what exactly scaling is? The proportional adjustments of the dimensions of an electronic device while maintaining the electrical properties of the device. That is, the size of dimensions or the dimensions of the device are going to be reduced, but keeping the electrical properties of the device should be same. So if you see the VLSI technology, it is constantly evolving towards smaller line widths and feature size. So day by day the line width is going to be, the width of the gate is reducing. So finally the size of the MOSFET is going to be reduced. And this reduced feature size generally leads to better performance and more gates per chip. So as the size is going to be reduced here, the speed of the MOSFET is going to be increased and number of gates per chip is going to be increased. So due to this scaling, what are the properties that are going to be affected? Properties of IC we'll see. So impact of scaling is characterized in terms of several parameters. The parameters here are minimum feature size. Mainly the size of the MOSFET, basic size of the MOSFET is going to be reduced. Number of gates on the chip. So on a particular chip, the gates that can be accommodated can be increased. Power dissipation. Obviously the power dissipation is also going to be reduced because of the scaling. Maximum operational frequency. This is going to be increased because of the shrinking of the MOSFET, number of the MOSFETs can be accommodated on the chip. So the distance between the MOSFETs is going to be reduced, so the frequency is going to be increased. And the die size, finally the die size is going to be reduced a lot. Production cost also reduces because more number of chips can be done at the same time. Scaling models. Now we'll discuss about different types of models for scaling. We have totally 3 types of scaling. The first one is constant electrical field scaling, second is constant voltage scaling, and the third one is general scaling. So when we say constant electrical field scaling, this is the ideal model. Here both the dimensions and voltages are scaled by the same scaling factor. Whereas when you say constant voltage scaling, here the dimensions scale but the voltages will remain constant. When we say the general scaling, this is most of the realistic scaling for today's situation. The voltages and dimensions scale with different factors here. So the factors of dimensions is different and the factor for voltage is different. For example, here if you see the MOSFET, this is the basic structure of the MOSFET, which is N-type MOSFET here. So this is our P-type substrate, N-type source and drain, and this is the gate region. So the length here is nothing but length of the MOSFET is this one L, and this is the width of the MOSFET. Here if we see the length, width and the thickness, all these are reduced by alpha, whereas the dimensions are going to be reduced by beta. So this is reduced by beta and all these factors are reduced by alpha. So in order to accommodate the scaling models, 2 scaling factors are used, one by alpha and one by beta. 1 by beta is nothing but the scaling factor for supply voltage and gate offset thickness, whereas 1 by alpha is the scaling factor for dimensions, both horizontal and vertical dimensions. So alpha is related to dimensions and beta is related to voltages and gate offset thickness. So now we will see the effect of scaling on different parameters of the scaling, and different parameters due to scaling. For example, the first parameter what we consider here is gate area. The gate area is nothing but simply the length of the gate into width of the gate. So if we see lengths and widths are scaled by alpha, so the total AG, the gate area, is scaled by alpha square. 1 by alpha into 1 by alpha, which becomes 1 by alpha square. The gate capacitance per unit area, C0 or Cox. We know that Cox is defined as epsilon ox by D. So here epsilon ox is a constant and D is the weight oxide thickness, which is scaled by 1 by beta. So therefore the Cox is scaled by 1 by beta, which is equal to beta. Gate capacitance, that is CG. The CG, we know that it is defined as Cox into length into width, and therefore the CG is now scaled by already L into W means 1 by alpha into 1 by alpha, and Cox is beta times. So therefore the total CG equal to scaled by beta by alpha square times. Similarly, the parasitic capacitance. The parasitic capacitance is defined as Cx, which is equal to Ax by D, where D is the depletion width around the source or drain. So we know that the D is scaled by 1 by alpha, and Ax is the area of the depletion region. Since it is area, it is scaled by 1 by alpha square times. Therefore, the total Cx equal to Ax by D, which is going to give now 1 by alpha here. Now carrier density in channel, that is Q on. The Q on is defined as Cox into Vgs. So average charge per unit area in the channel in the on state. So we know that Cox is scaled by beta and Vgs is scaled by 1 by beta. Therefore Q on equal to Cox into Vgs, which is scaled by simply 1. That means there is no change for Q on. Channel resistance. The channel resistance, we know that it is L by W into 1 by Q on into mu, where mu is the carrier mobility, and therefore here if we see R on, Q on into mu is there is no scaling factor for mu. Q on is 1 and L by W also 1. Therefore R on becomes, it is scaled by 1. Gate delay. Gate delay, if we say Td, which is proportional to R on into Cg. So the R on just now we have seen, which is 1, and Cg is beta by alpha square. So therefore the Td is now scaled by beta by alpha square. Maximum operating frequency. Operating frequency here is defined as W by L into mu into Cox into VDD by Cg. So, or we can simply say that F0 is inversely proportional to delay, 1 by Td, that is. So just now we have seen Td is nothing but beta by alpha square. So F0 becomes alpha square by beta. The scaling factor for the frequency becomes to alpha square by beta. Now saturation current. The current equation is, we know that the saturation current equation is mu n Cox into half mu n Cox W by L Vgs minus Vt square. So if we see the parameters here, IDSS is scaled by 1 by beta times. VGS and VT both are scaled by beta times. So therefore finally it becomes like 1 by beta square into here mu n into Cox by 2, that is beta. So finally it is 1 by beta. And the current density equation, which is J, is given as IDSS by A. So where A is the cross-sectional area of the channel. So we know that A is scaled by 1 by alpha square. So J is scaled by IDSS, just now we have seen, which is 1 by beta. Therefore completely J is scaled by alpha square by beta. Switching energy per gate, that is EG. EG equal to half Cg VDD square. So Cg is nothing but beta by alpha square times it is changed, whereas VDD square, since VDD is the voltage, it is scaled by 1 by beta times, so it is 1 by beta square. So the total value now becomes 1 by alpha square into beta. Power dissipation per gate. The power dissipation mainly comprises of two components, static component and dynamic component, where the static power is given by VDD square by R on, and dynamic component is by Eg into F naught. So if we see the total Pg static plus Pg dynamic, finally it is going to 1 by beta square times. Power dissipation per unit area. Unit area means power dissipation by area. So power dissipation is 1 by beta square times and area is 1 by alpha square times. So therefore PA now becomes alpha square by beta square times. And finally power speed product. Or power delay product. So since it is the product of power and delay, power is 1 by beta square times, and that TD here is beta by alpha square times. Therefore totally the power speed product is scaled by 1 by alpha square into beta. And this is the final summary of scaling here. Here if we see all these are the different parameters, and the effects here if we observe combined V and D. That means both the dimensions are scaled. Dimensions and voltages both are scaled here. So both beta and alpha are appearing here. Whereas if we see constant electric field, in case of constant electric field, beta becomes 1 here. So we'll be getting this one. So for constant electric field scaling, beta equal to alpha now. Therefore, all the parameters whatever are here will be changing like this one by substituting beta equal to alpha here. And whereas when we say constant voltage scaling, in this case beta becomes 1 here. Here only the voltages are going to be scaled, the dimensions are not scaled. So therefore beta equal to 1. So by substituting beta equal to 1 in this one, here we are going to obtain these values here. So finally, by using all the 3 scaling effects here, we will be getting different parameters and different scaling factors.